So I am recording. So what I want to do today is a couple things. First off, I do want to hit module 3 and talk a little bit about models because, well, first of all, let me start off. Any questions before we get started? Are there any questions, any issues going on, anything that you, we do have, I know if you were trying to do NetLabs yesterday morning, you may have found NetLabs was down. My data center lead took the NetLabs down. Nobody was on it, so he took it down and did a little bit of quick maintenance that had to be done yesterday. It was back up in about an hour and 15 minutes, but it is now up, knock on wood. And if you had an issue yesterday, I apologize. That we typically try not to have any downtime where I don't let you know about it, but sometimes it has to happen. So, but any questions or anything you want to add as we're getting started here talking about? Because I want to talk a little bit about, I use this very high-tech device called WordPad. That's a joke, by the way, y'all. But I want to talk a little bit about what's a reference model versus a protocol model, an actual protocol model. And in reference to this, when we talk about the reference model, we're talking about the OSI model. So if you ever heard the OSI model, that is a reference model, which means it doesn't, even though some of you may be like me, old enough to have been involved in networking long enough to remember, there was actually a protocol stack called the OSI protocol stack. It was never widely used, and it did follow the OSI model exactly, but the actual protocol model is the model that is used by a protocol that is in use or protocol stack in the real world. So that's the TCP IP model. And so both models, regardless of what is, whether it's reference or a true protocol model, both models are trying to describe how two devices communicate to one another. So the process of the sending machine or the requesting machine encapsulating a request, and then on the opposite side, that request being de-encapsulated. But the difference here is this. The OSI model, as you know, consists of 7 layers. It's got the application layer. Okay, it's got the presentation, session. What's the next one? Can anybody tell me? Application, presentation, session.
Network, data link.
Okay, well, you're missing one. You're almost there. You need the
transport. I'm sorry.
Transport. There you go. Transport layer.
Yes.
And then network.
Network layer and
data link, and then the last layer, which I call the blue collar worker, which is the physical layer. So it's just the bit pusher. So the 7 layers of the OSI model are application, presentation, session, transport, network, data link, or physical. Or if you need a mnemonic, from layer 7 to layer 1, it's all people seem to need data processing. If you need a mnemonic or an easy way to remember it, from 1 to 7, it's please do not throw sausage pizza away. Okay. This model is looking at how a piece of information is encapsulated and then de-encapsulated. Now, the TCP/IP model consists of 4 layers. It's the application layer, it's the transport, the network access, or excuse me, the network internet, sorry, forgot one here, internet layer, and then the network access layer. And we're going to see how these actually relate to the OSI model. But here's the important thing. The TCP/IP model is a real protocol model. And the way I describe the difference between a protocol model and a reference model is this. I'm one of those people that grew up years ago where kids put together plastic models. One of my favorite, I still put plastic models together because I play Warhammer and 40K, but one of my favorite things to put together were F-16s. So let's think about, if you go and buy the most expensive plastic model kit you can get for an F-16, you'll spend a couple $100 and it may have 300 pieces. How many pieces does a real F-16 have? Millions, okay? So consider the reference model like that plastic model kit. It explains how the communication process is going to take place, but it doesn't do it fully or in a real world way. A protocol model is how the actual communication is taking place. We're going to learn how these two models map to each other in this particular chapter, okay, in this particular module. Why do we even have models? Well, the biggest reason is because we need a way to discuss how two devices talk to each other. We need to be able to say, how does a message get from a sender to a receiver? And how is it encoded and transmitted so that it can be understood on the sending end? That is a protocol. Protocol is rule establishment. If any of you have been in the military, there are entire classes on protocol. You know, if you see the commanding officer of the base walking across the base, you don't walk up and go, hey, how you doing? It's not going to go well for you. So there are very strict protocols or rules. Same thing when we have communication between networking devices. There are rules that we follow so that the devices can easily talk to one another. We're going to look at message encoding. Again, that's how the message gets converted into, and that depends completely upon the protocol. How it's formatted and encapsulated. The size of the messages, that's all based upon what protocol you're using. Ethernet is roughly 1,500 bytes per an Ethernet frame. Timing and delivery options, all of those are part of network protocol requirements. So again, here is our encoding. You can see that for a normal communication between two people, if users try and describe a sunset, they've got to figure out a way to encode that so that the receiver can see that picture. Same thing with formatting and encapsulation. There has to be a way for things to get to the destination. We discussed the other day a little bit about IP addressing and about how IP addresses are like phone numbers. Well, we've got to have a way to get from one device to another. Part of that is our ability to address each and every piece of a conversation so that we know who the sender is and who the receiver is. That is handled by our protocol stack. Message size, again, goes back to how big of a message. If it's too big on the network, by the way, what we will end up doing is it will be lost or it will use up too much bandwidth. And also one of the problems you have is if you have a really big message and you send it as one big piece and you get 99% finished with it, and then there's an error, you lose and you have to retransmit all that. It's much better if you can actually break that large communication into smaller pieces and then send it as smaller pieces. Then if a piece gets lost, you only have to resend a very small piece instead of a large chunk of information. And that gets into our items such as flow control. You know, how do we say, oh, slow down, or response timeout if a packet's not received in a certain amount of time? All of these are set by the protocols themselves. And then last but not least is what we call an access method. And we're going to talk a great deal as we move forward about the access methods for Ethernet, which is carrier sense multiple access with collision detection, CSMA-CD. And we'll talk about how that is used to figure out how to place frames onto links so that we don't have collisions. Or if we do have a collision, how to recover from that collision. All right. So let's look at protocols. Again, protocols are just a set of rules. That's all they are. In our particular setup, network protocols are designed to allow us to send information between different devices. We have communication protocols like HTTP, which are the rules used to send and receive communications between a web server and a client. We have network security protocols like TLS and SSL. Those are where we get our secure right here. So we're actually securely connected. So I can click here and see that this is a secure connection with a valid certificate. We have routing protocols like OSPF and EIGRP and BGP, and the older versions like RIP, V1, V2. And then we've got other protocols that are like service discovery protocols, and those are like DHCP, CDP, LLDP. All of those are different protocols. Typically what we do have is we have what is called a protocol stack. And a protocol stack, this is a group of protocols working together to allow communication. And we're going to learn, for instance, in TCP/IP, you've got HTTP at the application layer. It rides on top of TCP, which rides on top of IP, which rides on top of whatever layer 2 particular protocol you're running. It could be Ethernet or whatever. So this could be Ethernet, which runs on top of whatever type of layer 1 media you're using. So it could be fiber, it could be wired, it could be wireless, all those. So that is a group of protocols working together. So if I go to request a web page, I'm actually using the TCP/IP protocol stack in this group of protocols right here to make my request, to get that GET request, and then to have that sent back to me from the web server. So right here is a great example. This is exactly what I was showing you. If I was to request a web page off of this server right here, I would do it with an HTTP request, which rides on top of TCP. So the application layer, it's HTTP. At the transport layer, it's TCP. At the internet layer, it's IP. And then at the network access layer, this particular communication is using Ethernet. And all of these protocols are working together. And one of the key things about these protocol models is that each layer provides services to the layer below it and receives services, provides services to the layer above it and receives services from the layer below it, but really doesn't know what's going on at the layers above or below it, which is why when we look at some of our OSI model descriptions, they get confusing because it may say there's error checking going on at layer 2, and there's also error checking going on at layer 4. But that's because layer 2, the data link layer, doesn't know that the transport layer is also doing error checking. So here's our protocol suite. It's a group of protocols working together. Here is TCP. It's been around for a very, very long time. It uses a 4-layer model, application transport internet network. By the way, you can remember this with a mnemonic of ATN, ATIN, or if you want to go bottom up, NITA, NITA. So you NITA to remember this, NITA. But you can see at the application layer, we have HTTP, DNS, DHCP, FTP, and that's only some of the ones that are at that layer. We've also got TFTP and others that's the application layer. The transport layer consists of the 2 protocols, TCP and UDP, which we will discuss in detail when we get out like module 15 or 16. The internet layer consists of IPv4, IPv6 plus ICMP, which is Internet Control Message Protocol. And then at the network access layer, one of the great things about TCP/IP and one of the reasons it has taken over is they, when they created the TCP/IP protocol suite, they did not specify any network access layer requirements. In other words, they didn't say that you can only run TCP/IP over Ethernet, or you can only run it over token ring, or only over wired Ethernet. They said, hey, as long as the network access layer will talk to the internet layer, we will allow you to use any technology that comes around. And so TCP/IP has been able to grow with all these new standards that have come out for faster and faster speeds at layer 2.
Kelly, is that also known as the DoD model?
Yes, this will be called the DoD model because the DoD created TCP/IP. Yes.
Well, that, and we don't like that many pieces, smaller pictures.
Right. Yep. So that is another name you see it sometimes. That's kind of fell out of favor. It's called now just the TCP/IP model, but it has also been called the DoD model in the past, most definitely. The 2 biggest ones we're going to talk about, of course, are the TCP/IP. The other one we are going to talk about is the OSI model, which are the 2 models I showed you earlier. So here's our example again. By the way, I showed this now 3 times. So it's pretty important that you understand that these are a group of protocols working together. All right. Here's the entire suite, or at least a majority of the suite, if you've ever wondered. So at the application layer, you've got DNS, DHCP, v4, v6, SLAC, which you will learn that SLAC is stateless address auto configuration. It's a way to get IPv6 addresses. SMTP, POP3, and IMAP. All those are email protocols. FTP, STP, SFTP, which is Secure File Transfer Protocol, and TFTP, Trivial File Transport Protocol. HTTP, HTTPS, and REST. REST is a type of API, RESTful APIs that are something you probably heard about.
Hey, Kelly.
Yes, sir.
So all of these things are exam questions.
Could possibly be. Yeah, you could possibly find this on an exam. Which of the following are application layer protocols for the TCP/IP model? Yep, that could be a possibility. You'll notice
Do they require the port numbers as well?
eventually, yes, we will learn the port numbers. And that's something that is in later modules. That's up in the top modules when we get up into module, I think it's 16 or 17, 14, module 14. So we will be learning port numbers. So.
Okay.
You also will learn which one of these run on which transport layer protocol. So typically, for instance, HTTP runs only on TCP because it needs to be connection oriented. Whereas DNS can run on TCP if it's between two DNS servers, or UDP if it's between a DNS client requesting information from a DNS server. So DNS is one of the few that runs on both TCP and UDP. Most of them run on one or the other. Down the internet layer, we've got all of these protocols. Now, I know they show routing protocols as being internet layer protocols. Some debate there. We'll go with it for now. Okay, we're not going to argue with it, but definitely IPv4, IPv6 are without doubt internet layer protocols. And then ICMP v4 and v6, again, without doubt, internet layer protocols. But then down here at the network access layer, notice there's really nothing that is TCP/IP related that is defined at this network access layer. This was intentionally left that way so that if you wanted to run it TCP over carrier pigeon, you could do it. By the way, that was an April Fool's joke one time. Someone actually wrote an RFC that was TCP/IP over a carrier pigeon network. So technically it could work. You just had to break everything down into really small packets and have a bunch of pigeons. So let's look at, here's the process. So this is a web server responding back with a requested web page. So it's going to take that web page and make it data at the application layer. All right. It will then put a layer 4 header or TCP header, transport layer header on it. Then it will put a layer 3 header, which would have the IP addresses of the source and destination. And then it would put a layer 2 header, which would be the Ethernet. In this case, it's running Ethernet, which have the source destination MAC addresses. And then that would be sent over to the web client. So this is a response to the client requesting a web page. Now we're going to learn as we move forward a lot more about what's in each one of these parts. But it's important to note that at each header, there are different items that are added. Like at the Ethernet header, you've got your source, your destination, and your source MAC addresses. At your IP header, you've got your source and destination IP addresses. At your TCP header, you've got the source and destination ports and protocol that's in use. All of that we will discuss as we move forward in class. All right. So let's look at our organization, some of the open standards. These are some of the groups that do these standards or create these standards. IEEE, INA, TIA, all of those. All right. So the IETF is responsible for creating many of the protocols that we work with and the standards we work with. And then INA and Internet Corporation for Assigned Numbers, Names and Numbers actually is what is responsible for handing out IP addresses in North America, in the United States. So for us, what we need to look at is the reference model. Now, first off, why do we even want to use a model? First off, for us as instructors, it gives us a way to discuss the communication process. So if I look at you and say, this is a layer 3 device, you know, okay, is it OSI model? Yeah, OSI model layer 3 device. You're going to say, okay, that's a network layer device, which means it deals with routing and its job is route determination or path determination. A reference model or models give us a way to discuss the communication processes and devices involved. It also gives us a way for vendors to create devices that will work together. So if we know how a layer 3 device is supposed to work, the vendor can build it to those specifications. It also helps with competition, because as long as the devices can speak the correct languages of the protocols, they should work together. Now, having said that, they don't always, but they should. And then for us, it's supposed to be easier to learn. So here's our 2 main models and how they map to one another. Now, this you've got to know. This is going to show up on a test or exam somewhere. You need to know the 7 layers of the OSI model and how they map to the 4 layers of the TCP/IP model. So the OSI model's application, presentation, and session layers all map to the application layer of the TCP/IP model. Transport and transport map 1-to-1. The network layer of the OSI model, which is layer 3, maps to the internet layer of TCP/IP model. And then the data link and physical layers map to the network access layers of the TCP/IP model. Need to know this. I would just go ahead and say, memorize this chart. Excuse me, know exactly how they map to one another. Now, the OSI model took me a while to wrap my head around. And I'm so glad now they show you this, because as you look at this OSI model and what each layer does, realize that it's not as clear cut as what the OSI model likes to make you think. That's why in a real world model, there's just application, which covers the function of these 3 layers. But the application layer, the way I teach it is this. I tell my students the application layer provides services to applications. Okay, that's how I teach it. Now they talk about even process to process communications. That basically means applications talking to one another. So that's the purpose of the application layer. The presentation layer is responsible for taking data and putting it into a intermediary format if it needs to be. It also, one of the things, if you do a lot of reading on the OSI model, most readings say that if encryption or compression takes place, it's being actually done at the presentation layer. And the session layer maintains, establishes, and terminates sessions between hosts. Those 3 layers are very nebulous because they're all software. Now, the transport layer is also all software, but it's a little easier to explain. The transport layer is that what actually breaks individual pieces of the data down to, it segments data to the correct sizes to be sent across the network. And it reassembles that data for individual communication. And many times you'll hear and read in some books that the transport layer provides guaranteed delivery. Well, yes and no. In the reference model, yes, it does. In the real world, because we have TCP and UDP, the transport layer provides guaranteed delivery if you're running TCP. It does not provide it if you're running UDP. And that goes back to the difference between a reference model and a real world model. What they found out was, hey, it'd be great if everything could be guaranteed reliable delivery, but we don't need that. If I drop a couple pixels in a streaming video on Netflix, that's okay. It's all right that I do that. I don't want to retransmit that pixel and have that pixel show up 30 seconds later or even 3 milliseconds later. That would make no sense whatsoever. It would just create a ghost image. So there are some applications where UDP, which is a protocol that doesn't guarantee delivery at layer 4, is more appropriate. Voice over IP, same thing. If I drop a packet or one little piece of a packet, retransmitting it with voice over IP would make no sense whatsoever.
Kelly,
go ahead, Benjamin.
Do you feel that this is a critical start for a technical interview for students, or in terms of they need to have this memorized, or we need to really drill this into them so it'll be a second habit? I mean, give them like 5 tests on this because they'll see it forever. How do you recommend we get students to get this to stick in their heads?
Okay, here's why I think this is so important for students. I sit you down for a job interview and I ask you, okay, you have encountered a problem with a PC on a desktop. How are you going to handle that problem? All right. Now, if I'm interviewing somebody and that student says, well, first off, I'm going to ask what's changed. Okay, that's real world experience there because something's changed to make it break. But then if that student says, then what I'm going to do is I'm going to look at this from the OSI model or layers of the OSI model. First thing, I'm going to look at the physical layer. Is it plugged in? Okay. Then I'm going to look, do I have blinky lights? And I make jokes about blinky lights, and I wouldn't say that in an interview, obviously, but do I have a connectivity light at layer 2? So do I have a green light on my, so that's a data link connection. Then the next layer is, I'm going to troubleshoot now. I'll do an IP config. Do I have an IP address? So I think the important thing about this model is that it carries on to everything we do in terms of how we discuss devices. So another great thing, think about this, Benjamin, if I have a job interview and I ask you, okay, tell me what you know about a switch. And you tell me, okay, a switch is a layer 2 device that deals with frames, framing and access control. I know that you understand MAC address tables, that you understand what a MAC address is, or at least have heard of a MAC address. So I think this model and the TCP/IP model is such a useful frame for students to really build their IT knowledge around. Everything from troubleshooting to understanding devices in the network. So I think that's why it's so important. It's one of the, I will say this, I think if you look at CCNA 1, the most important thing that we're going to do in this entire CCNA 1 is IP addressing and IPv4 and IPv6 addressing and subnetting. That's the most important thing in this course. Right up there with it is understanding the OSI model and TCP/IP model and how they can be applied to so many parts of the IT field. So that's why I think it's important to stress this. I'm open if y'all think that's wrong or different. I mean, I trust me, I don't think I know it all, but I do think it's a reliable way to discuss the IT field and the many processes in it.
I agree with you.
Actually,
It's definitely one of those things that should be discussed across all IT disciplines in the first place as it relates to device communication, as you may reference, like other industry exams like Security Plus, A Plus, and Network Plus. Of course, those are some of the top, or this is some of the top detail that's discussed on those exams too.
Exactly. It's a fundamental, it really is for almost all certification exams. The OSI model and TCP/IP models are considered such fundamental, important theoretical information to know. I do stress, and that's one of the things I want you to do too, is to stress reference model. You know, this doesn't survive contact with the enemy. It's not in the real world. We don't have, you know, all 7 layers in use at all times. We have these 4 layers over here, but the same processes are being used to make it work. Okay.
actually
So-
give them scenarios and challenge them and tell them, hey, you got a layer 3 failure. What are you going to do?
Yep. And how would you troubleshoot a layer, or you get a request? You know, here's a great thing. You get a call from one of your users and they say they can't get on the internet. Well, first question is, okay, what do you mean by you can't get on the internet? Well, I can't open my email. Totally different problem there. You know, that's a different thing. You know, can you do an IP config for me and tell me what your IP address is? So it gives them a basis to troubleshoot around. So,
Kelly,
yes,
it sounds like you're almost
I dropped my drink.
advocating that with our build, we have a help desk, and a help desk may give them the ability to experience this on a regular basis. Is that a good way for us to look at this? Or
Yes. And in fact, what we do, a lot of our students, Benjamin, actually here, we try to get them on to the help desk at Stanley Community College to work with the IT department. But if you don't have that ability to do that, what I would suggest is you get your students into their later classes. It may not even be a bad idea to have a great example I'll give you is I'm the Skills USA coordinator for the state of North Carolina and build the state test and actually build the national test. But one of our key things we do there is we actually do a help desk support call. So we set up a little voice over IP system and we actually have the students do a support call. So I think it's important there that later as you get them, you know, once they've been through at least 1 and 2, maybe in CCNA 3, start doing some of those support type calls and getting them used to it, because a lot of the support call too is, hello, my name is Kelly. I work, you know, for Acme so-and-so. Can I get a callback number in case we get disconnected? 99% of the students today don't even know to say, hello, my name is so-and-so. Can I get a callback number? Those simple things that can really help them in job interviews. And will make them more effective as they go out and about trying to get jobs. But yeah, I would agree. I think having some type of help desk simulation or help desk, maybe not during the first part like this class at the very beginning, but toward the end, especially of CCNA 3, I would strongly suggest doing that type of work. And a project class would be a good thing. The network layer, folks, deals with path determination and logical addresses. We'll talk about IP addresses and the fact that they have no physical relationship to the devices they're being placed on. They're just logical addresses. The data link layer The data link layer deals with actual media access control addresses or MAC addresses that are burned into a NIC. And one thing I want you to know is this: the data link layer actually has two sublayers. It has a sublayer called the logical link control sublayer, or LLC, and the media access control sublayer. And one of the things that's interesting about these two sublayers is this: as you look at the OSI model, the physical layer deals with physical components, so cables, wires, transceivers, hubs, anything that's just layer one only. As you move up the OSI model, we're still dealing with media access control. We can plug a cable in a NIC. So a media access control network interface card, that is physical, but now a network address or an IP address is logical. So there has to be a point right here where we go between what is the physical components and the logical components. And that's what the logical link control layer does, the sublayer. And that the neat thing about this is, think about when they come out with IPv6, instead of having to rewrite the entire TCP/IP model, they just changed the logical link control sublayer to be an IPv6 LLC sublayer and tells it to talk at layer 3 to IPv6. So these two sublayers here, media access control deals with actually putting the frames onto the media. The logical link control deals with that interface with the upper level software components that are associated with the network layer. So, and we've got more on that later, but just be aware, I do want you to know it's got those two sublayers. So application on TCP/IP does all the things. Now look, represents data to the user plus encoding and dialogue control. Well, folks, that's these three layers right here. That's representing data to the user, which I would, instead of saying to the user, I would actually say represents data to the application myself. Encoding is the presentation layer and dialogue control is the session layer. Transport is exactly like the transport layer of the OSI model. The internet layer is best path and logical addresses. And then down here controls the hardware devices. So we're looking at data link and physical layers. Here's the second time they've shown you this slide. I've told you before, if you see something one time, it's important. See it twice, it's really important. See it 3 times, it's on the certification exam. So take that as you may. So let's look at how data is encapsulated. So as we are moving information across a network, I mentioned we don't want to send these huge pieces of data. It's much better if we can segment that data and take and make it into smaller pieces. And that way, if we lose a piece or a piece is damaged in transit, we just send that piece instead of the huge original data. We also want to be able to take and put that information onto the same wire and have multiple devices accessing it at the same time. That's called multiplexing. And we do that through layer 4 with segmenting sequence numbers and those types of things. And here's those sequence numbers. So we can actually put numbers on it. So if we break this big picture into 10,000 little bits, we got to know how to put the puzzle back together when it gets to the opposite side. The sequences are how you put the puzzle back together on the receiving side. Now, at each layer, we have a name that we associate with the information. So if we are at the application layer, we call it data. If we're at the transport layer, we call it a segment. If we're at the network layer, we call it a packet. If we're at the data link layer, we call it a frame. If we're at the physical layer, we call it a bit. So this is useful when discussing information, because if I tell you we have frames here, you should automatically know, oh, it's a frame. It's a layer 2 protocol data unit. If I say it's a packet, the problem with packets, it's used interchangeable a lot of times. Actually, a packet can be sometimes used by many people to be anything above layer 2. But by definition, packets are network layer protocol data units. Segments are transport layer, and then anything above that would be considered data. It's just a way for us to talk. Now here, again, is our encapsulation. So it's taking this information and putting it into our setup. Now, here's what I want to do real quickly. And again, my handwriting's horrific, folks, but it will. I'd like to show you this if I can, just so I can get the. We were doing some subnetting in my other class. All right, so let's look right here. We've got the application layer. Got the presentation, session, and a little better writing on this thing. Transport. Not much better though. Oops. Got the network layer, data link, and last but not least is the physical layer. Now, the reason I put this out here is because I want us to look at, we got a host here, got a host here. All right. This host A is going to request a web page from host B. So the request is an HTTP request. So we know that's application layer request. So what's going to happen is you're going to take that request and you've got, as the data is that HTTP request, and we're going to put an application header here. Then all of this information becomes data for the presentation layer. So this is now data. And we're going to put our presentation header. Now all of this becomes data. And we'll put our session header on here. All of that becomes data again. And what I want you to envision is and this our transport header goes here. All of this becomes data. Okay. Imagine those Russian dolls. You remember how the Russian dolls used to stack inside of each other? So now we're down to a network layer. So I'm going to expand it just a little bit so I can go down here and we're going to have a source IP. There's a whole lot more that goes in here, but this is a source IP address and a destination IP address. So we'd have to get those to go in here. And all of this becomes data. Okay. And then now we're going to have actually at the data link layer, we're going to have the destination MAC address, and we're going to have the source MAC address. And the reason I reverse those is because of the way Ethernet works. And we also add actually here a little thing called a CRC, or a cyclical redundancy check. And all of this becomes data, and really down at the physical layer, it just comes zeros and ones. Okay. That's sent across the link, and on the receiving end on host B, the first thing it's going to do is pull it up to layer, at least up to layer 2. And what it's going to do is it's going to look in there and it's going to look at the destination MAC address and say, is that my MAC address? If it is the MAC address for B, then B takes the header off. It actually will run the CRC, because there is a little CRC there to make sure it's been damaged in transit. A lot more about that as we continue forward. But it would then pull that off and pass it up to layer 3. At layer 3, guess what it looks at? The data's still there, right? That's still sitting in there. That's all those little Russian dolls that we've got. We've also got right here, still we've got our source IP and the destination IP. If that destination IP matches the IP for B, it takes this apart, pulls the header off, passes it up to the transport layer. At the transport layer, it continues to do the same, and it will take the transport header and look and see what protocol that is for, and will continue to de-encapsulate it until it can pass it up to our web server, which is running on B. So anytime there's a communication, the sending host encapsulates the information. The receiving host will de-encapsulate the information. And it's just like those Russian dolls. We put the information at the upper layer becomes data for the layer below it. And that is why each layer has no clue what is going on below it and what the other layers are doing, because it's just packaging it as data for all the layers below it.
Question.
Yes, sir.
Using the stack as we encapsulate the data and it gets down into the frames. If they're used, this is where it gets confusing for me, because there's the software out there that allows you to spoof an IP.
Right.
But you can't spoof your Mac.
Yes, you can.
So
yes, you
okay.
actually can. Yeah, there are multiple programs out there that will let you spoof MAC addresses. There are hacking tools out there that let you spoof MAC addresses all day long. So you
Okay.
actually can do that. They're
But if
basically
they're not
packet
spoofing
crafters.
both, there really isn't an anonymity that goes along with spoofing just one of them.
Right. Yeah.
Because I would expect that it's all going to be in the metadata anyway.
It would be. I think the thing there would be if it's spoofed, if they've spoofed the IP and spoofed the MAC address, you're not really going to be able to find where it came from easily.
Okay.
No.
Thank you.
But you can spoof both. You can spoof both, and it's fairly easy to do. There's all kind of little packet spoofing programs out there.
Yeah, I've seen the IP stuff and had that happen. I haven't seen the MAC stuff.
Yeah, you can do it. And in fact, one of the crazy things you also can do, there are programs out there that you can use to create thousands of bogus MAC addresses, and you flood the MAC address table on a switch, and then that switch will start acting like a hub because it's got a flooded MAC address table, which is kind of, well, not kind of, very dangerous. You can solve that with port security, but it is possible that your switches can be attacked that way.
Okay.
So that's what's going on here, by the way, when they show this communication becoming data. So it becomes data, and then they put the TCP header on it. You'll notice they just skipped the application presentation session headers because this is TCP. So they said the application layer is the data. Here's the transport layer header. Here's the internet layer header, and then the network access layer header is the Ethernet information. And then here's de-encapsulation. We're on the receiving end. It looks at it, ensures it is for the receiving host, de-encapsulates it. Questions about that? Questions about the idea of our address. Now, one of the things we do have physical addresses, which are MAC addresses, and those are burned into the MAC address or burned into the network interface card. I used to joke and say you should always go to like a yard sale and buy yourself an old used wireless NIC in case you need a throwaway NIC. But the other thing you can do, obviously you can spoof MAC addresses, but each MAC address is burned into the network interface card and should be unique worldwide to that particular network interface card. It's a little different when you're doing virtual machines. Yes, Benjamin.
In the CCNA training, do they have any of the cloud stuff or containers and Kubernetes? Is that in there anywhere? Is that considered something completely different?
There's a little bit in CCNA 3 we'll go through that has talks about network programmability and talks about a little bit about containers, but very little about containers. I think I was meeting with Foresight Tech this week, and I think y'all are working with them with some Red Hat stuff. There's a really good containers and Kubernetes class in Red Hat now.
Okay.
That
Yes.
you can take a look at. But it's mentioned in this, but it's not really covered all that much. I'll be honest with you, I want to take the Kubernetes class and container class for Red Hat because it looks really good. So logical addressing, here we have the idea of logical addresses, which are layer 3 addresses. So source destination IP addresses. We'll talk all about how we get those and how they're used as we move forward in this class. So devices on the same network. Now this is kind of interesting because we're going to look at how devices on the same network can communicate to each other. One of the important things that you need to know is you need to know both the source and destination MAC addresses. Well, if you are a local device and I need to talk to you, I can send out what's called an ARP request. I can just send an ARP request and say, I need to know who with the IP address of 192.168.1.9, what is your MAC address? And then you will send me back an ARP reply. Then I will have the information I need to be able to send you your frame. How do we find the IP address? Well, typically that's with DNS. So if we're trying to go to a particular server, in this case, we would know the FTP server was on 1.9. But if we didn't know that, we would have to do a DNS lookup. So we do ftp.stanley.edu. That would be resolved via DNS to the IP address of 192.168.1.9. The sending host would then say, do I know the MAC address for 1.9? If the answer is no, then we would do an ARP request. We have an entire section down here on address resolution. So we'll talk about that. If it is not on the same network. So like if it's on the same, no problem. We send an ARP request, get an ARP reply. If it's on a remote network, the problem becomes in that we have to send an ARP request, and those are broadcast. And routers don't allow broadcast to pass through them. So routers will do what is called a proxy arc. In other words, the router will respond that its MAC address is the correct MAC address for that remote host. So even though I'm trying to get to 172.16.1.99, I'll never really know its MAC address because my local gateway will say, ooh, that's an ARP request for a remote host. We can't send that as a broadcast. So I proxy my MAC address as the destination. And then the router will handle that request and it will be routed across the internetwork. And one of the reasons why the destination MAC addresses go first is because you think about the process I showed you with encapsulation. One of the very first things the client has to do is take every frame it receives and look and see, is this my MAC address? By putting the destination MAC address first, it allowed the clients that are looking at these frames to be able to do it faster. They don't have to look at the source MAC and then look at the destination MAC. They can look at that very first MAC and say, oh, that's not for me, and discard it. And that is exactly what happens. If a frame comes into a device and it's not for that device, so the MAC address, destination MAC is not it gets discarded. Okay, so that's pretty easy there. Now, one thing you'll notice is that at every single hop, the router is rewriting the layer 2 information. So the layer 3 information will stay the same because the communications between 1.110 and 1.99. But in order to meet the source and destination MAC addresses in this hop right here, you have to rewrite layer 2 between these two routers. And same thing over here, you have to rewrite it again at layer 2. So every single hop of a router, layer 2 information is completely rewritten to match not only the media or medium that's being used, but also to match the addressing of that link. Layer 3 is not rewritten. Now, we all know about NAT. Layer 3 can be rewritten, but for the CCNA, we don't really discuss that to begin with. All right. Now, folks, this lab right here, installing Wireshark, one thing I'm going to warn you about, we are really, all I want you to do with this is install Wireshark and just look at some traffic locally. If you are on your campus network and are not allowed to do this, you can install it on your local PC at your house and just capture some traffic. Really, we're just trying to get you to see how Wireshark works. How many of you worked with Wireshark before? Any of you?
Loosely.
Yep, I've worked on it a little bit.
Okay. Wireshark's a neat protocol analyzer. It's free, but it is a protocol analyzer. So your campus policies may forbid you from running Wireshark on your campus network. So that's why, as far as for this lab, as long as you're able to install Wireshark and capture some traffic, I'm fine. I'm not trying to get you to get in any kind of trouble, or anything like that. All right. Any other questions? All right. Let's look just quickly at the physical layer, because I think this is a pretty easy module for everyone. We're going to look at the physical layer, which is to make ones and zeros, to connect to the cabling and make a connection to the device. Just like I showed you last week, I showed you our console cables and how you connect to a device. The network interface cards are connected with our cables. Now the physical layer is all ones and zeros. And when we look at physical layer characteristics, one of the things, these are typically created by the ISO, EITIA, ITU, or ANSI or IEEE. And the physical layer are physical components. So like an RJ45 connector, a piece of cable, the process of encoding. So the process of taking like Manchester encoding, where 0-bit has a high to low volt transition and a 1 is a low to high volt transition. So say anytime there's a transition from low to high, that is considered a 1. Anywhere there's a high to low, that is considered a 0. Some encoding schemes use the presence or absence of a particular voltage. It just depends on what particular encoding standard you're using. It varies. So 100 base TX uses 4B, 5B encoding, and 1000 T uses 8B, 10B. And I don't know the exact specifications on those. We would have to look at those. I don't think that's something your students need to learn other than learning that it is encoded. And it's important to note the encoding is based upon a time slot. So it's some measurement or some change during a time sliver that is important. So on a copper cable, we're going to have the presence or absence of voltage. On fiber optic cable, we're going to have light or no light. And on wireless, we're going to have amplitudes. We can have actual amplitudes, or we can have other types of oscillations per unit of time. That is important. Now, this concept is very important, and I've got a couple terms I give you here. All right. The first one is bandwidth. So let's talk about bandwidth, and I'm going to give you a great example to think about this. You've got a garden hose, okay? Your garden hose is 1 inch around. Your bandwidth is 1 inch worth of water. So your bandwidth is the maximum amount that can travel through a media or medium. So that's the maximum amount, the max that can travel over a media or medium. Okay. If you've got a 4-inch fire hose, you can get 4 inches worth of water through it. All right. Throughput is the amount traveling over a media or medium. Okay. Just because you've got a garden hose that's 1 inch around doesn't mean you turn it wide open. You may only have it halfway open. Your throughput is the amount of water going through that hose at a given time. Now, good put is something we don't really talk about with garden hoses, but it's the amount of data minus your control traffic. Because one thing you need to realize is that just because you've got a 1 gigabit link, that doesn't mean that a gigabit of data is flowing across that particular link. There's always going to be retransmissions. There's going to be routing protocols. There's going to be CDP, Cisco Discovery Protocol, or LLDP. So good put is the amount of data that's going across your actual connection. And then we have two other concepts that are associated with physical cabling, and that's attenuation. What is attenuation?
Noise.
What'd you say, Steve?
Noise.
Noise. Attenuation we typically call it the loss of signal strength as the signal travels along a medium. Now, if it's copper, that's due to impedance, right? If it's can also be due to crosstalk. Crosstalk, you remember crosstalk is another term I like to put in here. And crosstalk is signal overflow from an adjacent wire or adjacent source. Could be EMI, electromagnetic interference from lights. It could be EMI from a motor or from a high energy source. So when we talk about different physical layer components, we talk about these terms. So bandwidth, the max that can go across the particular cable type. Throughput, the amount going across the cable at any moment in time. And then good put, the amount of data that is actually being moved. Attenuation is the loss of signal strength. That is why attenuation is why we can only go 100 meters with unshielded twisted pair, because past that length, we have the chance of having too much of a signal loss to be able to have an efficient signal. And then crosstalk is why we have to use special types of cabling. So here we have again latency. That's the end-to-end amount of time it gets, including delay from one end to the other. Throughput, the amount of traffic going through at a particular time point. And good put, the amount going over that is data, usable data being moved. Let's look at copper cabling. So here's some copper cabling looking at electromagnetic interference. By the way, a great creator of EMI is a nuclear weapon. If you really want to be scared to death, you need to read the book 1 Second After. It's actually based or written by a professor who used to work at a college up in the North Carolina mountains, but it talks about the effects of an EMP attack on the United States. What would happen if a 50 kiloton nuclear weapon was basically exploded 50 miles above the atmosphere on the east and the west coast, and how dramatic of an effect that would have. Just recently, I don't know if you've been reading, the sun has entered into a new phase of sunspots, and that's another massive danger for our electricity grids and for our communication satellites and everything going on, because it creates all types of problems. So here's our different types of cabling for copper cable: unshielded twisted pair, shielded twisted pair, which can be, there's a couple different ways you can do this. You can actually end up with each individual pair being shielded, and also then shielding the entire thing. You'll notice one of the things that's neat about these pictures is, notice you can even see the different rate of twist in the unshielded twisted pair. The reason for this is to help prevent crosstalk. If the twist is different, the idea is that the signals on these wires will not interfere with one another. And we've got good old coaxial with its non-stranded single copper core. Unshielded twisted pair, easy to use, cheap, very non-resistant to EMI, but it's probably our cheapest and easiest to work with. Shielded twisted pair, still fairly easy to work with, but it is not as easy because you've got these shielding inside of here, but it is more resistant to EMI. And then coaxial is more resistant than UTP or STP, but it is much harder to work with, and we don't use it as much. Now, these are the cable connectors for unshielded twisted pair, for coaxial. BNC or British Naval connectors, or bayonet connectors, depending on where you read it, N-type and F-type. So we're using this mainly now for satellite and some types of cable modems. Properties of UTP, again, we've got this cancellation due to the twist. We've got our cabling standards that we have all the way from Cat 3 up to Cat 8, which are showing the different standards being supported. We use a lot of Cat 6 in our data center to run 10 gigabit connections from our servers to our switches. Uses, that's a very bad picture of an RJ45 plug, because they look like a big phone plug, not like a squat thing there. This is funny because if you've been with the Academy program long, when we used to make cables all the time, you saw a lot of these. But the correct way that you should terminate a cable is with the actual cable sheath up into the RJ45. All right. The big thing that I want you to take away from this section is the idea that we do make, and there are two different types of standards, 568A and 568B. The main difference is the reversal of the green, white, green, and the white, white, orange, or orange, white, orange. They are reversed in the A and B standard. If you want a straight through cable, you make both ends one standard. If you want a crossover cable, you make one end an A, one end a B. If you want a rollover, you literally make one end an A or B, and then on the other end, you just roll the tab away from you. Typically, when you put the RJ45 tab on, you put the tab away from you. But if you want to roll over, you put the tab away from you on one side, use the exact same layout on the other side, and flip it back towards you. We used to have to really worry about this, but with all across now, we don't worry that much about it. We just use a straight through cable for almost everything. The other item here is fiber optic cable and how important it is. And the big thing here is it is used between buildings or anywhere EMI is a problem. Single mode has a single glass core of 9 microns and has a single path for light. Single mode typically uses lasers for its to be able to send the light pulses. Whatever you do, never, ever, ever look into a piece of fiber, no matter whether someone promises you it's not connected to something, because it can blind you instantly. Also, never put it against your hand to see if you see something, because some of these higher powered lasers could actually burn you. Multi-mode is uses actually still a glass core, but it's a bigger core, and it allows for multiple paths of light. Multi-mode typically does not allow as far runs up to 550 meters, whereas single mode can go kilometers at a time. In fact, you can go undersea cables that run thousands of miles with amplifiers inside of them. We use fiber for long haul or anywhere we're trying to avoid electrical problems. So for instance, on our campus, we're on the top of a hill, so lightning is a big issue. So we use fiber between the buildings to make sure the lightning strike doesn't, we don't turn our campus hill into a big, a large antenna, basically. It also, in fact, today, my wife's business had fiber brought into their building, and it's giving them gigabit fiber. So that is starting to happen. It used to be, I wish we were working on fiber to the home around here, but yeah, who knows if it will ever happen. Different connectors, I call these ST simple twist because you push them on and twist them. The SCs, I call simple click because they click in. So STs are twist, SCs are clicks. LC is like a simplex click. And a lot of times now we're starting to see this where they're actually dual LC connectors. And one of the things you will learn about fiber is there's always a send and a receive fiber with fiber optics. So you got send and receive fiber, they always come in pairs. And here's some of the patch cables. Here's a simple click because these click in. And then here's also a LC, but it's the two and they click in. Here's one that's an old school simple twist to a simple click. So it just depends on what you need to use. We also now have SFP fibers, which are available to use for SFP plus connections. The beauty of fiber optic is it has really theoretically no limit on bandwidth. We don't know how much it can support. It's all based upon what we can put into the fiber. It has massive distance runs, completely immune to EMI and immune to any type of, no problem if you do. I'm about to finish up, Dr. Hugh. But you'll notice that fiber optic cable, really the big thing I teach my students is if it needs to be super secure and it needs to be resistant to EMI, put in fiber. Otherwise, we're probably internally going to be using UTP. All right. And then on wireless media, we're just going to look here for a second, and it's just looking at the different standards. And the big thing with wireless, we have an entire section on it later, but looking at coverage areas, looking at your building, looking at whether or not the building, for instance, the building I'm in right now is actually two buildings that were built at different times joined together, which means just behind me is actually two external walls, which makes it very difficult for our wireless connectivity to work. But that's why we have wireless access points in the front of the building and the back of the building to allow for that. So that is the end of our section on the physical layer. So I'm going to actually stop sharing now, and I am through with the lecture for today. Are there any questions?
Yes, Kelly. How useful do you think it is if for a class, if we took them on a field trip to a telecom?
I think it's very useful. I think it's extremely useful because to be able to see how those how it's actually connected in the real world is something that even I struggle with at times, especially if they can see, how a DSLAM works, and how actually, your fiber, the fiber is connected to the point of presence and those types of things. I think it's very important.
I think those are hard to arrange, right? Because of
Yes.
security.
Yeah.
Because I know.
Well, that and COVID now.
Yeah.
Nowadays, it's real hard.
Yeah.
Okay.
But even before it was tough because of security concerns. Yeah. But it's something that I would try to do, especially when things get a little bit back to normal. I'd definitely try to do it. Okay. Any other questions?
Hey, thank you so much.
You're very welcome. Thank you all. I will get this posted up for everybody. And if you do have any questions, please let me know and send me an email. And otherwise, just keep working. And if you have any problems, obviously reach out to me.
Have
Thanks,
a terrific
everybody.
day.
You too.
Right.
Everybody
Thanks.
stay safe.